Thank you all to come today, and thank you, Trevor, to agree to give this webinar. I would like to start the webinar by acknowledging the traditional custodian of this land, that in my case are the Bedigal people. I would also like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islander who are present here today. So it is my pleasure to introduce Dr. Trevor Campbell, who is our guest today for the Bayes SSA webinar series. Trevor is an assistant professor of statistics at the University of British Columbia. After a degree in engineering science at the University of Toronto, Trevor did his PhD under the supervision of Professor Jonathan O at MIT, working on truncated Bayesian nonparametrics. In particular, working on nonparametric mixtures. And then he moved under the supervision of Associate Professor Tamara Broderick, still at MIT, to work on projects for automated and scalable Bayesian inference. So Trevor is a prolific author on computational statistics. He's a bit at the boundary between statistics and machine learning. And today he's going to present his work on parallel tempering on optimized path. So I will be monitoring the chat. We suppose that like most of the questions, all the questions will be asked at the end of the webinar. But I will still monitor. So if there is anything very technical and specific during the webinar, I will ask the question. So just use the chat. And another thing is that if you don't want your name to be, so this webinar will be recorded and the recordings will be available. So if you don't want to be named particularly, specifically, just write it in the chat because the chat is not recorded. So thank you very much, Trevor, to agree to give this seminar today, and the floor is yours.
Awesome. Well, yeah. Hi, everybody. And thank you to Clara for the invitation and to the Statistical Society of Australia. It's a real pleasure to be here. Today, I'm going to be talking about some hot off the press work on parallel tempering, which is a sort of meta MCMC algorithm for performing Bayesian inference in complex, multimodal, high-dimensional posterior distributions. I should say that this is joint work, and in fact, the primary contributors here are these two really, really fantastic students, Saf and Vittorio, both of whom are PhD students at UBC. And this is also joint work with my wonderful collaborator, Alex Bouchard-Cote. So I suspect many of you are, maybe even all of you are familiar with the paradigm of Bayesian statistical inference, but I figured I'd do a quick once over anyway, just in case. So in Bayesian statistics, we have some data, let's call it X, and I want to infer some unknown parameter of interest, theta. And I treat both of these two quantities as random variables. And I consider the conditional distribution of theta given X. As Bayesians, we typically call this the posterior distribution. And this gives us a wide range of options for coherent point estimation, like the maximum a posteriori or the mean of the posterior distribution, and also uncertainty quantification. So we can consider, for instance, the variance of the posterior distribution or the entropy or any number of other things. Here I'm writing a density, a conditional density. In this talk, I'm assuming that everything is simple enough that everything has densities. And so you can see that I'm writing the conditional density of theta given X for my posterior. And we can write this in terms of more tractable quantities using Bayes' rule. So here I have the likelihood, which is the probability of a particular value for my observation X given a value of the parameter theta. And the likelihood distribution allows us to build interpretable complex generative processes into our statistical models. The sort of unique feature of the Bayesian approach is the prior distribution. And the advantage here is that you get to build in prior expertise. So whatever you know about the problem going in advance, you can work that into the prior distribution. Now, if I look a bit closely at this formula, you'll see that there's this normalization constant that's kind of a problem, the 1 over p of x here. And so we can't just do this multiplication in practice. We have to jump through some hoops. The major challenge that we want to address is to deal with this posterior distribution. We want to sort of understand the distribution. And we can generalize that statement and just say that my goal is to compute expectations of some function of my unknown parameter theta under the posterior distribution. The way we typically do that in Bayesian computational inference is through sampling. Now, I can't directly sample from this posterior distribution. I usually have to take a sort of more circuitous approach. In particular, the most common thing that practitioners do these days is they create a Markov chain, so a random walk through your space of all the values of theta. And that Markov chain is designed very carefully so that the random distribution of the location of the state converges to the posterior distribution. In other words, if I close my eyes and I run my Markov chain for a really long time, my understanding of where the state of the Markov chain is corresponds to my posterior distribution or something close to it. And then I open my eye and I look at the state of the Markov chain and I record that as a sample. In practice, what people typically do is they just run their Markov chain. They throw away the first fraction, let's say 30% of the states that the chain generated to get rid of that initialization bias. And then they just take the rest of the states as if they were samples from the posterior. The problem with this approach is that it can often have trouble with complex, multimodal, high-dimensional targets. One very common example of an issue with standard Markov chain Monte Carlo algorithms is when you have a multimodal posterior, the Markov chain can kind of get stuck in one of the modes. So if I initialize the chain from this location, it might just randomly sort of walk into this mode and just bounce around this mode. And remember, because you just see the states in this chain as the samples from the posterior, you're just going to miss this mode entirely. And of course, the same thing can happen with the other mode. Another problematic case for a lot of Markov chain Monte Carlo algorithms is where the scale of the posterior distribution actually is different in different parts of the parameter space. So for instance, if I design a Markov chain that sort of moves around nicely in this part of the space, the steps may be too big for this lower area, and the chain may never actually make it into this sort of funnel shape. And of course, the list goes on. There's many, many more examples of structures that don't work well for a lot of Markov chain Monte Carlo algorithms. In this work, we're going to talk about parallel tempering, which is a way to deal with these sort of more complex distributions. And the idea is that we're going to sample, instead of just from the distribution we care about, we're going to try to sample from a path of distributions, and then we're going to swap the states along the path. So for example, I can pretty easily sample from this nice isotropic Gaussian distribution that I've drawn the contours for here. And I'm going to construct a path from this nice distribution, the reference, towards the target distribution of interest, which in this case is this multimodal thing. Once I've decided on a particular path of distributions, I'm going to run Markov chain Monte Carlo algorithms in all of them, every single one of these along the path. And for each one, I'll get a bunch of states, and I'll be swapping the states between neighboring pairs of distributions. And for instance, because it's easy to find samples in this area for this particular distribution, if I swap with this distribution, you can actually reasonably explore this part of the mass in this distribution, even though it's cut off from the rest. Now, the big question in this work is, what path should we use? There's a standard choice in the literature, and I will demonstrate that this is, generally speaking, not a fantastic idea. In particular, I'm going to introduce the idea of parallel tempering on optimized paths. I'll introduce a flexible family of nonlinear paths of distributions. I'll introduce an algorithm to optimize within that family. Along the way, we'll do a little bit of theory on the efficiency of a path and what that means for parallel tempering. And all of the above, those developments will show that this new method actually breaks previous theoretical upper bounds on the performance of past PT algorithms. So if that wasn't enough, there's this really, really cool application of Bayesian statistics that's been happening recently on imaging black holes. And in particular, the physicists who worked on this problem actually used parallel tempering for the Bayesian statistics part of their analysis. So just to give some cute background, because this is really fun, this is Messier 87. It's a galaxy. It was imaged by Hubble. And at the center of Messier 87 is a black hole, a supermassive black hole. You can even see the plasma jet that's being emitted by the black hole here in blue. That's 5,000 light years long. The black hole itself, and most black holes look something like this, right? So you have this, what you can see is the event horizon here. And circling around this is what's called the accretion disk. It's a bunch of matter that sort of swirls around the black hole. Now, the amazing thing about this is a simulation. The amazing thing about this image is that it shows you how light bends around the black hole because of its intense gravity. So you can see that actually in reality, this looks like Saturn. It's just a flat disk around the black hole. But because of the gravity, you can see that the accretion disk looks like it bends up and over the black hole here. It doesn't. It's just the light coming from the top surface of the disk on the other side that's bending around the black hole back towards you. And similarly, this on the other side, this lower ring, that's actually the bottom side of that disk, right? So this image blew my mind. I think this is just the coolest. Anyway, for Messier 87, the mass of this thing is 6.6 billion times the mass of our sun. And the radius is 26,000 times roughly the radius of the sun, which means that this is big enough that we actually have a hope of getting a picture of it. And in particular, we're interested in imaging the accretion disk. Just last week, this team of physicists that's been using these algorithms, the PT algorithms, they just put out a new image of the polarization of the light in the accretion disk around the black hole. There's a lot of uncertainty here. There's atmospheric measurement noise. There's imperfect antenna calibration. The big struggle here is weak identifiability in the posterior. This is what's creating these very complex shapes in the posterior. And that's because the likelihood, actually, it turns out there's a Fourier transform in the likelihood that's kind of underdetermined when you try to do the inverse. The big punchline here is that this is a very difficult posterior to explore, and they used this algorithm from Saf's, so the first author on this paper, Saf's earlier PT work. So I thought that was really cool. It was a good little motivational example for why you might care about PT. But now with the motivation out of the way, let's actually get down to business. So in parallel tempering, to set this up, we have a reference density, pi naught. We have a target density, pi 1. Our goal is to sample from pi 1. That's what we would like to do. In order to use PT, we construct a path of distributions from the reference to the target, pi naught to the power 1 minus t, times pi 1 to the power t, and t varies between 0 and 1. So in light blue here is the reference, dark blue, let's say, is the target. And as I vary t from 0 to 1, I get a sort of sequence of distributions that interpolate from one to the other. How does PT work in terms of the actual steps, the algorithmic steps that you're taking? Let's just focus on two distributions in the sequence here. So distribution n and n plus 1. Each distribution has its own Markov chain Monte Carlo algorithm that's running. So each one has its own state, which I've colored in blue and red. Parallel tempering generally has two moves that you have to consider. The first is exploration, where you apply any Markov chain Monte Carlo single update to each chain. So here you can see that I've moved my blue state over here, and I've moved my red state over here. That's totally in parallel. There's nothing special there, just run MCMC for each one. The special part of parallel tempering happens in the second step, which is communication. What you do is you actually try to move the blue state to this chain, and you move the red state back a chain. Okay, so the way that we do this while preserving the fact that all these distributions or all these Markov chains should be sampling from their stationary distributions is we formulate the swap as a Metropolis Hastings step. And the probability of accepting that step is, well, the minimum of 1 and the densities evaluated at the swapped states divided by the densities evaluated at the original states. So how does this work with more than 2 chains? Because of course we need to swap along all the chains in the path, right? Let's draw out a couple of chains here. So here I've got 1, 2, 3, 4, 5 chains in black, blue, orange, purple, and gray, going from the reference at the top to the target distribution at the bottom. The idea here is that we have to propose swaps between distinct pairs. So I can swap reference and chain 1 at the same time as I can try to swap chains 2 and 3. I could also do the same for 1 and 2 and 3 and 4. And at every step of the parallel tempering algorithm, you do one exploration move, and then you do one communication move, and that's that swapping. Okay, and the way that you decide which of these two pairs to go with is you just randomly decide. Okay, so at step 1 of the algorithm, I might try to swap these two, and you can see that the black state and the blue state actually interchange. The orange state and the purple state don't. That swap was rejected. And then we continue this. So I might randomly sample the same set of pairs. Here, the blue and the black, that swap was rejected. The purple and the orange, that swap was accepted. And in the next iteration, I might actually find that I chose the different pairs to swap. And of course, then both look like they were accepted here. If I draw a line through a state of a single color, so I'm watching what happens to a state as it sort of gets swapped back and forth between all the chains, that sort of tells me how well the PT algorithm is moving states around, how well it's interchanging information. So that leads to a question: how do we evaluate a PT algorithm? The typical things that you might do as a statistician are things like effective sample size. We don't want things, metrics like that, because they're influenced by exploration. If I use a better MCMC kernel for exploration, I might get a higher ESS. If I want to just evaluate the performance of PT itself, the fact that I'm doing this path of distributions and swapping, I need something else. The way that people do this in the literature is to use something called round trips. So basically, when I have a state that starts at the reference, and of course, as I move to the right, I'm doing communication steps and exploration steps, I'm running PT. And if I watch where a single state goes as I do these communication steps, if it starts in the reference and it makes its way all the way down to the target and comes all the way back up to the reference, I call that a round trip. And the round trip rate is the frequency at which these round trips happen. This is how I measure the performance of a PT algorithm without worrying about the details of the individual Markov chain Monte Carlo algorithms that we're running in each of the chains. Okay, so a PT algorithm works well when I have lots of round trips, when the algorithm is swapping states very, very quickly and efficiently. Let's look at what this kind of diagram might look like in a real practical application. Okay, so once again, I have my reference at the top, I have my target at the bottom. I have, in this case, 30 chains. And on the right, moving to the right, I have iteration number. So this is a figure that I took from Saf's paper last year. It's studying a Bayesian change point model. The important thing here is that if I watch a single state, just like I did on the previous slide, and I watch kind of where it goes as the communication rounds are running, you can see that the state never makes it from the reference to the target. I mean, it certainly never does a round trip, but it never even makes it halfway there, right? Something is going on here. In particular, the path seems to exhibit a random walk kind of behavior. As it turns out, there's a very, very simple fix to this problem by Okabe et al. In 2001. The idea here is that instead of randomly picking pairs to swap at every iteration, you do it deterministically. So you do the even pairs, and then you do the odd pairs, and then you do the even pairs, and then you do the odd pairs. So if I do my little diagram again here with the black, blue, orange, purple, and gray states, let's say I tick-tock between the choices. So first I do the 0 and 1, and the 2 and the 3. And then in the second step, I do the 1, 2, and 3, 4. And then I go back 0, 1, 2, 3, and I repeat this process. If I then draw those lines again through the states, you can see that what happens is I actually, assuming everything gets accepted, what actually happens is I get consistent lines of motion, right? The black state seems to just kind of work its way down to the target. And meanwhile, the gray state is working its way back up to the reference. Same with the purple state. Orange state is going down to the target. It's a very simple fix. The theory behind it is really beautiful. And in practice, it helps a lot. You can see that if I do this deterministic even-odd swapping scheme, that I actually do get a round trip in this particular example, right? It started at the reference, made its way down to the target, came back up to the reference, and that's a round trip. Okay, so the non-reversible, what's called a non-reversible scheme, tends to perform significantly better. Theoretically speaking, we can analyze what happens as the number of threads, the number of parallel chains goes to infinity. As it turns out, in the random reversible method, as n gets large, the performance, the round trip rate actually decreases. This is because of that random walk behavior. As you increase n, you need to make your way through more and more and more chains to get from the reference to the target, and it's not moving very efficiently. Meanwhile, in the non-reversible method, you get a constant performance as n goes to infinity. And so this brings parallel tempering into the realm of usefulness as a sampling mechanism. Great. So NRPT solves the problem, non-reversible PT, right? We don't need to do anything anymore. Job done. Well, hold on a second. Let's take a look at a very, very simple example. I have a Gaussian distribution as my reference and a Gaussian distribution as my target. The standard deviation is 0.01 for both of them. I have -1 as the mean for my reference and 1 as the mean for my target. I use 50 chains. I use the perfect exploration, IID, right? I'm sampling perfectly from these Gaussians. And I'm using my linear path that I described before. Let's take a look at the number of round trips that we get in this incredibly simple example. If I plot the number of round trips on the y-axis and the number of iterations on the x-axis, in red, I'm showing the reversible random choice method. In green, I'm showing the deterministic even-odd tick-tocking method. And in black, I'm showing the best possible theoretical upper bound on the deterministic method, so the better of the two. It's not too difficult to see here that after about 50,000 iterations, we have not had a single round trip in either method. And not to mention, I mean, beyond that, the upper bound that we get here is about 100. So even if we were massively lucky and this, the problem was set up perfectly, we would still hit about 100 round trips after 50,000 steps. So what happened here? Let's dig into the math a little bit to see what's going on. So if you recall, the probability of accepting a swap between any two pairs of chains, let's call that alpha n, it's the minimum of 1 and the densities evaluated at the swap states divided by the densities evaluated at the original states. Let me just flip that around a little bit, and I'm going to define the rejection rate for chains n and n+1. That's Rn, and it's equal to 1 minus the expected value of alpha n, where I'm sampling from the two chains. Let's pretend I can sample exactly from these two, right? So this is the probability that a swap is rejected, Rn. Saf's work last year showed that in this setup, the round trip rate is equal to 2 plus 2 times the sum from over all the chains, basically, of the rejection rate for chain n divided by 1 minus the rejection rate for chain n. Take all of that, inverse. So of course, if I have rejection rates that are close to 1, right, if a lot of samples or swaps are being rejected, then this is going to be quite small, close to 0. The term inside the brackets will be quite large, and so the round trip rate will be quite small. Beyond that, we actually have maybe a slightly more insightful result that says that, okay, let's forget about the choice of n. Let's just take n to infinity. I have as much parallel computation as I want. In that setting, the round trip rate actually converges to this constant that I mentioned earlier. Lambda here we call the global communication barrier. If lambda is large, then of course that represents a difficult parallel tempering problem. And if it's small, that means that the round trip rate is high and it represents an easier problem. So in our cute little example that we just did with the two Gaussians, you'll notice that the reference and the target are nearly mutually singular. They don't share a lot of mass. They don't overlap very much. In this setting, the global communication barrier lambda is actually quite large. Here is the linear path again between the two Gaussians, right? And I've discretized 1, 2, 3, 4, 5, 6, 7, 8 chains in this little picture. And you can see that with this reasonably large number of chains, I don't actually have too much overlap between any pair of these distributions. This is especially bad for Bayesian statistics because it's very standard to have a problem like this. Typically, the reference distribution that we use is the prior. The target distribution that we use is the posterior. And most often, the prior is not very well specified as far as comparing to the posterior is concerned. These are often mutually singular. So then, okay, is the problem just fundamentally hard, right? I mean, we haven't done anything super wrong here. Is this just a difficult problem? And I mean, I hope not, right? Because these are just two Gaussian distributions. If I can't do PT between two Gaussian distributions, I'm kind of in big trouble, right? So then the question is, can we do better? Let's analyze this problem a little bit more. So I have my Gaussian reference and target. The standard deviation here, I'll call that sigma. And the two means, I'll call them mu naught and mu one. In this setting, Z is the absolute difference between mu naught and mu one divided by sigma. This kind of captures the amount of overlap between these two distributions. If Z is large, they don't overlap very much. We show in our work that the linear path in this setting has a global communication barrier that is roughly linear in Z. Okay, so if Z grows, lambda grows. The problem gets harder for a PT. On the other hand, there exists a path of Gaussian distributions such that the global communication barrier is log Z. What that means is that even if we just restrict ourselves to thinking about paths of Gaussian distributions, we can do at least exponentially better than the standard linear path in terms of the round trip rate, right? Asymptotically in n, because lambda is that global communication barrier, it's related to the round trip rate. Okay, so we can do at least exponentially better. That's, I mean, there's room for improvement here, right? This is not just a fundamentally difficult problem. And the idea that we have is that we're going to change the path so that actually, I mean, a pretty good intuition here is that as we sort of interpolate from point A to point B, we're going to squish the distribution down and then unsquish it and bring it back up. Okay, we're going to anneal the distribution and then unanneal it. The point here is that if I make a path that looks instead like this, there's quite a bit more overlap between successive distributions, which means that the rejection rate will be lower when I try to swap states between them, which means that the communication barrier will be lower, which means the round trip rate will be higher, which is what I want. Okay, so our goal now is to try to figure out how can we construct a path of distributions that looks more like this than the linear path. All right, so we need to start thinking about more general paths than the linear path. Let's set up a definition here. So I'll say that an annealing path for a density pi, that's a target, is a map from the interval 0 to 1 to densities pi t. And I need it to satisfy a few things. The first is that the right endpoint has to be my target. If I evaluate my map at t equals 1, I have to reach my target distribution. Second, I have to be able to write my densities along the path, pi t, as a exponential of an unnormalized log density function, wt. And wt has to be piecewise twice differentiable in t. So my path can look something like this. It can have some kinks here and there, but overall it has to be sort of a smooth continuous path, only with a few potentially problematic areas. Finally, and this is with a big asterisk around it because the paper has much more detail on this, we basically require that the log density, this wt function, has the derivatives have finite moments. Okay, in the paper, there's the real technical version of this. Don't treat this as correct in any way. But this is kind of the intuition, right? We just need that w can't be, the path that w creates can't be too curvy. We can't have sort of an arbitrarily high curvature in some part of the path. Reason being is that we're going to eventually approximate this thing with linear splines. And so if you're using linear splines, if you have really, really high curvature, they won't well approximate the path. So that's sort of the intuition. So this is a pretty big net to cast, right? General annealing paths. Can we think of a couple of examples in this class? One that's very straightforward is the mixture path, right? So if I construct pi t to be a mixture of my reference pi naught and my target pi 1, and the mixing weights are 1 minus t and t. If I do this, my path looks something like so. I start from pi naught, and then I slowly shift the weights from one component to the other, pi 1. This is probably not a fantastic path for parallel tempering, right? Specifically because of this step here, right? As I go from this distribution to the final one, there's absolutely no mass here. So it's going to be very hard to swap states between pi 1 and this distribution. Okay, what else can we do? Let's try what I would call a squish, shift, unsquish path. And now this has some kind of complicated piecewise expression. I start at my reference pi naught, I squish the distribution down, I shift it over, and then I unsquish back up to the target. So this is probably a little bit better for parallel tempering, right? Because every pair of distributions along the sequence shares a good amount of mass, right? They're sort of lying on top of each other. So okay, fine. This seems to be kind of what we're aiming for. How can we actually restrict ourselves to work with only the sets of paths that are good? So let's establish some desiderata for paths. The first and arguably one of the more important ones is that it should be general. The path that we design shouldn't be specific to a particular choice of the reference and target. Of course, if I give you a specific choice of reference and target, you can design a very, very clever path for these two distributions. What I want is something that is general purpose. The linear path is really nice here, right? Because it doesn't matter what the reference and target is. You just raise them to a power, raise the target to a power, and then multiply them. Of course, these have to be normalizable, but that's a fairly weak requirement. The second is that my family of paths should include the linear path as an option. Reason being is I don't want to do worse than the linear path in PT, right? So I should do at least as well. And in fact, typically we initialize the path optimization at the linear path. And finally, whatever path I design, it should allow me to squish the distribution down and then bring it back up. I have to be able to anneal, right? And the point is that I need to be able to achieve this high overlap that we talked about earlier. The way that we do this in this paper is that we construct an exponential family of distributions out of the reference and target. So here's my reference pi naught, my target pi 1. I raise pi naught to eta naught, and I raise pi 1 to the power eta 1. These are just two real numbers. If I do that, then eta naught and eta 1 are natural parameters of an exponential family. And I can just sort of vary them in R2. In fact, I can make both of them quite small, right? And that would actually help me anneal between these two distributions. Now I need a path of distributions. And so instead of just considering one value of eta naught and eta 1, let me think of a function of eta naught and eta 1. Okay, and the input varies on the interval 0 to 1, and it gives me a bunch of natural parameters. This is really nice. It's not specific to a particular reference or target distribution. It obviously includes the linear path because I can set eta naught to be 1 minus t and eta 1 to be t. And it actually enables us to anneal because I can set eta naught and eta 1 to both be very small. So what I've done here is I've converted our situation into the problem of designing a path of densities, which is very difficult, to the problem of designing a path in R2, a path of natural parameters, which is significantly easier. Now, this is still a very broad class of paths to work with, right? So let's maybe even make this a bit more practical and tractable. Let's consider a linear spline. And the linear spline function is going to have k naughts. Why should we use linear splines? As it turns out, if you remember, when we're doing parallel tempering, we have our reference, we have our target, we have some path of distributions between them. All that PT sees is the discretization of the path. It only sees 1, 2, 3, 4, 5, 6, 7, 8 chains. So according to PT, this may as well just be a linear spline. right? It doesn't actually know that there's a curvy path underneath the sequence of distributions. So let's just use a linear spline for our path. If we do that, this is a plot of an example of what we might get. So in this figure, I have my two natural parameters, a to 1 on the y-axis, a to 0 on the x-axis. The bottom right corner is the coordinate 1, 0, and so that is the reference. The point 1, 0, or sorry, 0, 1 here, that is all the weight on the target, and so this is, of course, the target distribution. The linear path that we've been talking about gets its name from the fact that in this space, it just draws a line between these 2 points. And even if I just add a single knot to my spline in the middle, and no, okay, so k equals 3 because I have 1 at the end point as well. So this is a total of 3. These two are fixed. This one is sort of, I can choose where this one goes. Even if I can just add this 1, I can actually achieve what we asked for before. Because this distribution, let's say, is the reference. This intermediate distribution exists at this knot point, and it interpolates between the two. And then, of course, the target is the final unsquished distribution. Okay, so instead of going along this linear path, I'm traveling along this spline. And it turns out that you can achieve this nice sort of annealing and shifting at the same time behavior that you would want. So the sort of last, I guess, technical question, how do we optimize this thing? The obvious choice is the round trip rate, right? Let's, we characterized before that the round trip rate is the thing that we care about when we're optimizing PT. So let's just maximize that thing. Well, step one is let's figure out what the round trip rate is for a general path. So recall, this is our formula for the round trip rate, tau n. It's 2 plus 2, sum over all of the chains, the rejection rate for chain pair n plus 1, divided by 1 minus that rejection rate. As it turns out, the way that this formula is derived is just, it's just derived by analyzing the discretized path with the schedule of distributions on it. In fact, nowhere does the path actually show up in this analysis. So in fact, the round trip rate for the nonlinear path is exactly identical to the round trip rate for the linear path, the formula that is, right? So it doesn't matter whether your path is sort of wild and curvy like this, this formula still holds absolutely true. Okay, that's good news. We don't need to really do any work. So can we then just, I'm running my PT algorithm, I'm getting samples from all of my chains along the path. Let me use those samples to estimate these rejection rates. And then I'll take the gradient of that and then use that to optimize my round trip rate. That is what we tried. Unfortunately, that does not work particularly well, as it turns out. The reason for this is that the round trip rate, the gradients that you get from this noisy estimation procedure, the signal to noise ratio is really, really low. And the noise, even worse than that, the noise is kind of heavy-tailed. So you can't really estimate the average particularly well. And so your optimization is just going all over the place. This is especially true, and I would say maybe even only true in early iterations when you're starting with a really bad choice of the path. And it kind of arises because of this denominator in this fraction, right? When in early iterations, all the rejection rates are going to be really high. You don't have a very good path. You're basically rejecting all of your swaps. So Rn is going to be close to 1. So this fraction is going to be quite unstable. And of course, estimates of it will be very high variance. So if I look at my cute Gaussian reference and target example, my mean of my reference is at 0. My target distribution mean is at mu. And if I plot that signal to noise ratio on the y-axis, so this is the standard deviation divided by the mean for the gradient. And on the x-axis, I have that position of that target distribution. You can see that the signal to noise ratio actually decreases as mu sort of moves off to the right. You can see why that is, right? Because as I move mu off to the right, the distributions in the chains are getting spaced farther and farther apart. The rejection rates are all going up to 1. And so the estimates of this round trip rate are becoming more and more unreliable. Okay, so round trip rate, not a good start. What about the asymptotics in N? Can I analyze maybe the properties of just the path itself, right? If I let N go to infinity, so I assume in a perfect world, I have as much parallel computation as I want. I can do a really fine discretization of my path. What does my round trip rate look like in that setting? As it turns out, in the nonlinear path case, you actually get a very similar result. The round trip rate converges asymptotically to 2 + 2 times the global communication barrier, inverse. Now, the global communication barrier has a generalized formula for the nonlinear path. Okay, so you can see that it's a 1/2 times the integral from 0 to 1 along this path, t ranging from 0 to 1. And we have an expectation of the absolute difference between the derivative of my log density evaluated at 2 samples, xt and xt prime, that are IID from my path distribution. So this looks kind of like an expected difference in gradients, or like rate of change of gradients or something like that. If you kind of squint at this and pull out your differential geometry textbook, you'll notice that this generalized communication barrier looks kind of like a path length for PT. Now, in practice, we can't actually compute lambda, right? Because you'll notice that it requires me to take samples from pi t for all t between 0 and 1. And I'm running parallel tempering. So I actually only have pi t for these discretized points along the path. So instead of this lambda, what we actually use is what I'll call lambda n. And it's the exact same path integral, just on the linear spline, instead of the curvy, the curvy underlying path. Finally, to make this a bit more reasonable for optimization for technical reasons that aren't worth getting into, we actually put an upper bound on this, this linear spline path integral lambda n. And it turns out there's a really cute upper bound that you can get. Basically, lambda squared is bounded above by the sum of the pairwise symmetric KL divergences. So if I look at each pair of chains along my linear spline path, and I add up the symmetric KL between all of those pairs, that again, it gives me sort of a notion of path length in terms of the efficiency of PT, and we're going to minimize this SKL upper bound. So does this actually fix the problem with the signal to noise ratio that we saw before? And the answer is yes, spectacularly so. In fact, the signal to noise ratio for the symmetric KL divergence objective along the path, it actually gets higher as the two distributions get separated from each other. The essence here is that the symmetric KL cares about tails because you're taking the log densities, right? Whereas the round trip rate, you'll notice it's like its acceptance ratios, which are always between 0 and 1. And so when you go into like the tails of distributions, you're seeing numbers that are sort of vanishingly close to 0 or vanishingly close to 1. Okay, so the SKL is much, much better behaved, especially in early iterations when you want to start from a really bad path and optimize towards something that's good. One thing worth mentioning is that you'll see that for good paths, the round trip rate objective may actually have a higher signal to noise ratio than the SKL. And so there's some opportunity here that we didn't investigate this, but you could, switch to optimizing the round trip rate in later iterations to actually, push the objective function that you care about. And finally, I haven't said anything about optimizing the locations of the points along the path, the schedule. And the reason for that is that we just rely on past work for that. There's a schedule tuning procedure that we use, and that's from Saf's paper about a year ago. So our focus is on optimizing the path itself, and then we just use this algorithm to choose where to put the points on the path. Okay, so rolling back all the way, we realized that the linear path doesn't work super well for PT in cases where the reference and the target are almost mutually singular. We developed a general class of paths. We found that within that general class, linear splines seem to be a pretty good idea. And then we developed a symmetric KL divergence upper bound on the objective that we're going to use to try to optimize that path. So let's run that algorithm. We're going to, at the same time as running PT, we're going to use the samples that we're getting to estimate gradients, and we're going to manipulate the spline knots along that path. So here's our trusty Gaussian example again. Reference the normal at -1 with a standard deviation of 0.01. Target is a normal at 1 with the same standard deviation. Once again, I'm showing you the same plot I showed you before. Red and green are the two methods, non-reversible and reversible, deterministic swaps versus random swaps, using the linear path. The dotted black is the best possible round trip rate, best possible number of round trips using the asymptotic theory. And as we use our optimized spline paths, what you see, and what I've done here is I've drawn a bunch of different spline paths for different numbers of knots. The punchline here is that it kind of doesn't really matter how many knots you use. Even 2 is good enough for this, or sorry, 1 in the middle, that one that I showed you earlier, is good enough for this problem. Basically, for the first, let's say 10,000 iterations, you can see that the optimization is kind of figuring out where to put the knots in the path. And once it kind of figures that out, all of a sudden the round trip rate shoots up and you start getting a very appreciable number of round trips as the iterations proceed. By the time you've done 50,000 iterations, you have something like 2,000 round trips. So this is a much more efficient PT algorithm. Here I'm plotting the objective function, the loss, as a function of the number of iterations on the x-axis. And I'm showing in blue the inverse round trip rate. This is the thing that we want to optimize, but we can't. Orange is our symmetric KL surrogate objective. This is the thing that we do optimize. The point of this figure is to show that as the orange decreases, so does the blue, right? By optimizing the orange, we're actually implicitly optimizing the blue, which is what we really care about. That's the round trip rate. You can actually also see very visually from this plot the noisy behavior of the round trip rate in early iterations. These spikes are very problematic for optimization, whereas the symmetric KL seems to behave much more reasonably. This spectacular result, in my opinion, is well, it's not special for this Gaussian example. Now, these are two kind of cute setups. So we have our beta binomial model. This is, again, a very simple conjugate Bayesian model, but the exact same pattern shows up. The green and the red are our two linear path algorithms. They don't do super well. They don't give you a lot of round trips. The black dotted, this is from the asymptotic theory. This is an upper bound that you can kind of expect to achieve. And the blues are all the different numbers of knots of splines that we've optimized. And again, you can see at the beginning, it kind of takes some time to figure it out. And then the slope kind of increases once it's found a good path and you start getting a lot of round trips happening. Same thing for a mixture model on the Shapley galaxy data. We actually studied a much more complicated mixture model than this one with, thousands of latent variables and things like that. And we recovered the label switching that you would expect to see from the true Bayesian posterior that you typically can't see from a standard, let's say, Gibbs sampling algorithm. Okay, so I guess scrutinizing these is not super important. The important thing is that you see this exact same behavior between all of these examples that we've tried, where the round trip rates, when you have a poorly misspecified prior and you use that as your reference, optimizing the path can actually give you an appreciable number of round trips, whereas not optimizing the path leaves you with a questionably performing PT algorithm. The final point that I want to make on the experimental results is how they scale with dimension. So let's use our trusty Gaussian example again. Here I have a normal distribution as my reference with the mean at -1, -1, -1, -1 up to d dimensions. And the covariance matrix is 0.01 times the identity matrix. The target distribution is 1, 1, 1, 1, 1. And again, with the same covariance matrix. In this result on the right, which I'll explain in a second, we're just fixing the number of iterations, 50,000. And as we increase the dimension, we're actually increasing the number of chains. right? So, and the reason is we're keeping them the same between the two algorithms, so it's a fair comparison, but we need to increase the number of chains because otherwise we don't see any round trips in any of them. Because as you increase dimension, the problem gets really, really difficult. So on the y-axis here, I'm plotting the round trip rate. Higher is better, as usual. On the x-axis, this time I'm plotting the dimension of the problem. So I have 1, 2, 4, 8, 16, etc., growing sort of exponentially. Light blue, I have my spline path with 4 knots. The dashed black is the asymptotic theory upper bound for the linear path. And the dashed green is what I actually get from the non-reversible PT, the better of the two linear path algorithms. As you can see, the problem does indeed get harder as dimension increases. But the benefit of using an optimized path versus a linear path actually increases. The distance between these two curves actually grows as you get to higher dimensions. In other words, the path optimized PT method is a bit more robust to dimension than the linear path PT. And of course, we expect that PT will be most useful in high dimensional problems. So we really do want as strong performance as we can in this kind of setting. And I think that's it. Just to wrap up, in this talk, I sort of did a brief review of PT and why you might want to care about it. It enables inference with intractable, multimodal, kind of complex geometry posteriors. And the thing that people typically do with parallel tempering, the standard linear path between the reference and the target, it has a very, and provably so, suboptimal communication efficiency. And in this work, we introduced the idea of optimizing the path on which PT runs. We gave a new theory of the efficiency of general paths. We introduced a flexible family of spline paths that you can use that are black box. They sort of apply very, very widely. And we also introduced a optimization algorithm that tunes the path for you. I've got here the link to the archive preprint. As I said, it's hot off the press. It was only recently put up. And there's a QR code here. If you don't want to type that in, just take your phone and scan it. You can open up the archive page. And I think that's it for